Hi, here we discussed about a project, design of an efficient PRPG for testing an approximate multiplier using truncation. Here, random number generation plays a critical role in modern digital systems, especially in cryptography, secure communication, authentication protocols, and hardware security applications. In these domains, unpredictability, speed, and reliability are not optional, they are fundamental requirements. FPGA-based random number generators are particularly attractive because they offer architectural flexibility, inherent parallelism, and high-speed operation. However, many existing FPGA designs face significant challenges. These include high hardware complexity, increased area overhead, long critical paths, and the need for complex post-processing blocks to improve randomness quality. True random number generators, or TRNGs, that rely on metastability provide high entropy sources. However, they typically suffer from limited throughput. On the other hand, pseudo-random pattern generators, or PRPGs, are fast and hardware efficient, but inherently deterministic and highly dependent on seed quality. Most existing research focuses either on enhancing entropy sources or on improving post-processing mechanisms. Very few works efficiently combined both approaches while maintaining low hardware cost and high performance. To address these limitations, this work proposes a high-throughput FPGA-based random number generation architecture that integrates a metastability-driven TRNG with a lightweight PRPG-based entropy expansion scheme. The PRPG structure is derived from a static segment truncation-aware, or SSM, design, originally developed for approximate multiplier testing. In this work, it is repurposed for randomness generation. However, the SSM-based implementation results in higher logic utilization, increased power consumption, and reduced randomness quality due to excessive zero-noise patterns in multiplication outputs. The key novelty of this work lies in replacing the SSM structure with a truncation multiplier integrated with a multiply-accumulate architecture within the same TRPG-PRPG framework. This modification significantly reduces hardware utilization and shortens the critical path delay while maintaining comparable power consumption relative to the SSM-based design. Experimental results confirm that the proposed truncation-based architecture achieves efficient entropy generation, high throughput, and strong scalability. Functional verification is performed using ModelSim, and synthesis, timing, and power analyses are carried out using Xilinx tools, validating the effectiveness and practicality of the proposed design for security-oriented FPGA applications. Now we can verify this paper. This paper we taken as reference for PRPG with static segment multiplier architecture. Here, too, we'll showing the architecture of SSM multiplier. This static segment method multiplier is an approximate multiplication technique that reduces hardware area and power by conditionally truncating operand bits. It divides each n-bit operand into two segments and uses a smaller m times m exact multiplier, where m is less than n. This figure 7 shows the architecture of PRPG. This figure shows the proposed PRPG architecture designed for testing the SSM approximate multiplier. Instead of using a full n-bit LFRS, the design uses an m-bit LFRS with a phase shifter. This reduces hardware area because the internal multiplier of the SSM is only m by m bits. A 2-bit shift controller, implemented as a small counter, cyclically changes how the generated random pattern is connected to the operands. Depending on the counter state, the pattern is applied either to the upper segments, lower segments, or cross segments of operands A and B. This controlled switching ensures that truncation occurs evenly across both operands. When the lower segment is selected, sign extension logic copies the MSB to preserve correct signed operation. As a result, this PRPG achieves balanced test coverage, higher fault detection efficiency, and reduced BIST area overhead. Another reference of proposed TRNG will take from this paper, a high-speed FPGA-based TRNG using metastability. From this paper architecture, the FIG2 will used for to generate the seed for our PRPG. This work already improved with to reduce the metastability state with support of DCM and FSM operation. In this work, we propose a novel hybrid architecture that combines a TRNG with a PRPG to achieve high-quality randomness and high-speed random number generation. This is the proposed architecture of this work. Here, 32-bit architecture leverages the unpredictability of the TRNG to periodically seed the PRPG and enhancing entropy and addressing the limitations of standalone systems. This hybrid approach offers a scalable and secure solution for cryptographic and embedded system applications. Additionally, from the source paper, the PRPG developed with static segment method of multiplication, it will occupy more logic size and also produce more zero-noise error. For that, we proposed this PRPG with Truncation multiplier. This truncated multiplier is a hardware-efficient multiplier. It will useful to increases the trade-off accuracy and reduced the hardware cost, since this truncated multiplier will help to produce the output of n bits for n times n bits of multiplication. It will take less significant and some of the partial products are removed and also replace using the technique of deletion, reduction, and truncation. This work we have done in Verilog HDL and functional verification done with ModelSem and synthesize done with Xilinx Vertex 5 FPGA. Initially, we designed this PRPG with 2 multiplier module. This is the Verilog HDL code for PRPG with SSM. This is the simulation result. This is the Verilog HDL code for PRPG with Truncation multiplier. This is the simulation result. And the proposed architecture design of TRNG with PRPG. The Verilog HDL code also generate with SSM and Truncation multiplier method-based comparisons. This is the Verilog HDL core for TRNG with PRPG using SSM multiplier. This is the simulation result. Synthesis report. RTL schematic. This is the Verilog HDL core for proposed work of TRNG with PRPG using Truncation Multiplier. This is the simulation result. Synthesis report. RTL schematic. All the performance evaluation update in this comparisons table. Finally, we written an abstract document for this work. Title: Base Paper Abstract. Proposed title: Proposed Abstract. Existing system: Disadvantages, Advantages, Related notes. Finally, literature review and references. Thank you.
Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join Nxfee Innovation, shaping your future for VLSI research. Are you planning to publish your next innovative research in IEEE transactions on VLSI 2025? Welcome to Nxfee Innovation, where future-ready VLSI research projects are designed with novelty and quality for global researchers. At Nxfee, we provide novelty-based VLSI projects carefully aligned with IEEE transactions on VLSI 2025. These projects are not yet published, offering you a clear opportunity for unique contributions in top-tier journals. Our research covers key domains like low-power VLSI design, analog integrated circuits, FPGA implementation, signal processing architectures, and emerging applications such as cryogenic front-end ASICs, physical unclonable functions, and self-recycling SRAM cells. Each project comes with a verified novelty, simulation results, and complete customization for your journal publication. You'll find practical design files, HDL codes, schematics, and step-by-step explanations to guide your research journey. We provide 100% accurate results and comparisons of source code with all results, basic documentation, and explanation video. We provide execution support with explanation-recorded video explanations on your system. IEEE guidance for paper writing and journal publication. Affordable project packages with ongoing support. Customization to match your research needs. Early bird offers and discounts for researchers. Don't miss the chance to publish in IEEE transactions on VLSI 2025. Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join Nxfee Innovation, shaping your future for VLSI research.